Hello AAF kids. I am out today for a county meeting, so believe me, I'd much rather be with you. Please get out your homework and just quickly look over these slides. I have another video where I actually do all this homework with you. So if any of this homework was devastating for you, please do watch my video where I go through each one of these problems in detail and explain how I got each one of these graphs. Okay, so I just want you to quickly look over. Remember, rational functions aren't typical. Every quadratic looks like a U. Every linear function looks like a diagonal line. Rational functions can look broken, can look complete, can look like a line, can look like it has two pieces or three pieces, right? Or be continuous. So again, please do watch my video where I do every homework problem with you if these problems are devastating. We will be having a quiz next week on this. Remember, it takes some time to get used to these functions. Okay, so the substitute has a handout that looks like this, and I want you to fill in this chart. So for rational functions, we've been doing that thinking process, right? For how do you find the end behavior? Remember, horizontal asymptotes is really end behavior, right? Which means you plug in like -1,000,000 and like +1,000,000 and see what happens. The reason I taught you that process first, is because lots and lots of functions have end behavior, and this is what you need to do. But rational functions, which remember are a ratio of two polynomials, and we love polynomials, there is a shortcut that will always give you the horizontal asymptote behavior. And it's looking at the degree. This trick only works for rational functions because rational functions have a polynomial in the numerator or a polynomial in the denominator. Look at the degree. If the numerator is stronger than the denominator, and by the stronger I mean degree, you have no horizontal asymptote. So for example, if you have a horizontal asymptote that looks like 3x plus 1 over 2x squared plus 5x minus 7. All I'm looking at to determine whether I have a horizontal asymptote or not is that the degree of the numerator was a 1 and the degree of the denominator was a 2. Since, 3x squared over, silly me. I was doing the next example. If the numerator is like 3x to the 4th minus 2x cubed plus 7, and the denominator is 2x squared minus 4x plus 1, I'm looking at the degree of the numerator, which is 4, the degree of the denominator, which is 2. Since the degree of the numerator is greater than the degree of the denominator, I have no horizontal asymptote. And shh, don't tell anybody, but since an x to the 4th divided by an x squared reduces to an x squared with a positive leading coefficient, I know the ends of my rational function will behave like a parabola. Wow. Now there could be all kinds of crazy stuff happening in the middle, broken, not broken, but I know what the ends are going to be like. How about another example? What if I was 2x squared minus 3 over negative x plus 4. Now again, the degree of your numerator, 2, is greater than the degree of your denominator, so you have no horizontal asymptote, and plus, since x squared, and I could, the leading coefficient you can leave there or not, 2x squared over negative 1x reduces to negative 2x. I know the ends of my rational function will look like a diagonal line with a negative leading coefficient. Crazy! Next case, if you're bottom heavy, so the exact opposite, so for example, the one I was doing first, so for example, if you have x plus 4 over 3x squared minus 7, the degree of your denominator is stronger. So you have an x to the first over an x squared. So the numerator, 1 degree, is less than the denominator, which means you will have a horizontal asymptote, and further, that horizontal asymptote will be at 0. And you should be, again, able to reason this through. For example, if you've got, it means that as x gets really, really large, right, if you plug in 1,000,000 plus 4 into your numerator, but you plug in 1,000,000 squared minus 7, even if it's multiplied by 3, who really cares? The fact is that because you only have 1,000,000 in your numerator, but you have 1,000,000 squared, that ratio is getting really, really small and positive, right? Because the numerator is positive and the denominator is positive. So you're going to be sweeping towards 0 from the top on the right end and from the bottom at the left end, because if you plug in negative 1,000,000, your numerator is negative, but if you plug in negative 1,000,000 into your denominator and square it, it's positive. So what about the only case that's left? If the numerator and denominator are of equal strength, what happens, right? Think about your math, right? What happens when you have 3 over 2? What is that? What ratio is that? 3 halves, right? So what happens if I put 3 times 1,000,000 over 2 times 1,000,000? What happens to 1,000,000 divided by 1,000,000? Right? That goes to 1. So you're still left with 3 halves. What if it's negative 1,000,000 over negative 1,000,000? Doesn't that still go to 1? What if it's negative 1,000,000 cubed over negative 3 times negative 1,000,000 cubed over 2 times negative 1,000,000 cubed? What happens to a negative 1,000,000 cubed divided by negative 1,000,000 cubed? You are just left with 3 halves. So if you have the same degree, you still have a horizontal asymptote, but it won't be at 0. It'll be a ratio of the leading coefficients. So for example, what if you have 4x cubed minus 2x squared plus 4x minus 13 all over 3x cubed minus 4x squared plus 2x minus 17? Since the power of your leading coefficient, and who cares about the rest of the stuff? Remember, all of these terms mess with the middle. But at the ends, as x approaches positive and negative infinity, the higher powers take over and control the behavior of the function. And since x cubed divided by x cubed is 1, the ends will behave like y equals 4/3. You have just justified the existence of a horizontal asymptote, something that we'll be doing in a bit. Okay, so that's your trick. Now, let's talk about the domain. This is kind of old news. The domain of a rational function, and you should have a handout for this too with your notes. So I want to talk about two different ways to think about the domain of a rational function that I might test you on. Remember, the domain describes the existence of a function for all appropriate x values, right? You have to kick out values that make you divide by 0. Right? Since the rational function is only a ratio of two polynomials, you're not going to have any square roots, right? So you're only worried about dividing by 0. So if I give you a graph, you should be able to determine the domain. If I give you the algebra, you have to do a little thinking, right? Graphically, you have to look. Algebraically, you have to do some math. So here's a graph. It's a little bit disturbing that they don't have arrows. But can you tell what the domain is? All real numbers. Where's there no touchy, no crossy? There are no holes. So your domain is all real numbers, but x cannot equal 1. This equation is not this graph, right? I hope you can tell that already, right? These are two separate examples. Example 1, example 2. This equation is not this graph. So what is the domain? All real numbers except values that make you divide by 0. I don't care if there's any matching factors. I don't care about who's a vertical asymptote and who's a hole right now. I just care about the domain. Right? And I already factored it for you. You're welcome. Okay? Not so bad. The range is trickier. The range is trickier. It's not as bad graphically. Algebraically, it's a little bit of a dagger. This describes the existence of the function for appropriate y values. Now remember, y values depend on the x values. The range depends on the domain. So let's look graphically first, where we just have to look. Then we'll do the algebra, and it's the algebra that really is the uh-oh. Same graph. For the range, like the domain is so clear, right? Are you dividing by 0? Kick out of the domain. For the range, you have to make a list of suspects to kick out of the range. Who are your suspects? Your suspects are any horizontal asymptote and any y value of a hole. Those are your suspects. Suspect 1, suspect 2. Because remember I told you horizontal asymptotes are so nice and kind. Sorry about this random mark right here. They're so nice and kind. Like a vertical asymptote, don't you dare touch. Don't you dare cross. A horizontal asymptote, go ahead. Touch or cross in the middle, just not at the ends. So look at this function. Look. I see the horizontal asymptote. Where is it? That means the power of the numerator and the power of the denominator must have been the same, right? Because the ends are not pulled off to 0, they're pulled off to 2. So, the horizontal asymptote, is it, I know it's not touched over here at the ends, towards negative infinity and towards positive infinity. It's not touched. Is the horizontal asymptote ever touched or crossed in the middle? No. So, your range does not include 2. So check. I check the horizontal asymptote. Check the y value of any hole. Well, I don't have any hole. So there's no other y values to check, so my range is done. Okay? Not too bad with the graph. Uh-oh, what's that? What did I just add? A hole, right? Whoops, sorry. Let's just, since you're reading from a graph, you can just guesstimate. This looks like it's at about 2, 4. So for the range, what are your suspects? 1, ha. 2, y value of the hole. We already convicted the horizontal asymptote, right? Because the horizontal asymptote was not touched or crossed. We could see that. How about the hole, though? What's the y value of the hole? The y value of the hole is 4. Is the y value of the hole, look all the way across the function, is the y value of the hole ever used? Convicted. But look at this next example. What if instead what would happen, oops, sorry, I'm trying to erase my screen. What would happen with this function? I tried desperately to draw this well and it didn't go so well. Look at that one. Not only is the horizontal asymptote never touched or crossed, look, there's nothing down here. So my range is y is greater than 2 because there's no graph down here. It starts at the horizontal asymptote at 2 and goes up. But look at the hole. The y value of the hole isn't used here, but what about over here? Right? So my range this time is all real numbers, y is greater than 2. The y value of the hole is released. It was a suspect, but because it wasn't used over here, but it was used on this part of the function. Crazy, whack, funky, right? Now, algebra. This is really your uh-oh. For graphically, you do have to look closely. Now, I still have suspects. My suspects are 1, any horizontal asymptote, 2, any y value of a hole. So I'm going to start off range. What is the power of the numerator? Hint, it ain't 1. It's an x squared. What's the power of the denominator? X squared. What's the leading coefficient? X times x is 1x squared. X times x is 1x squared. So my horizontal, I have a horizontal asymptote at y equals what? 1. How do I know whether I kick 1 out of the range? Because as you notice, since no factor canceled out, I don't have any hole. So my only suspect is 1, and I don't have a graph to look at. So I don't know if the horizontal asymptote is touched in the middle. Well, there's only 2 variables in this equation, right? This is your y, and here's your x. What is this value? It's a y. So how about going and asking the equation? If a function has a horizontal asymptote and or a hole, how do you know if the y value should be kicked out of the range or eliminated from the range? The answer is algebra. Ask the function. Say, excuse me, ask it politely, excuse me function, will you ever equal 1? So plug a 1 in to the function and do algebra. This is called planning. This is why we did rational equations before this unit. So I'm going to do this work over here. Maybe you do it on the back. 1 over 1 is equal to x squared plus x minus 20 over x squared minus 3x minus 18. Now, this is actually, I don't actually need a lot of algebra. When is any fraction going to be equal to 1? It's when the numerator and denominator are equal, right? I can tell this numerator and denominator is not the same. So anyway, I'm going to multiply both sides by this denominator, right? So they'll cancel out over here, and then over here I'll have x squared minus 3x minus 18, right? Because that's what I would put here and here. Is equal to x squared plus x minus 20. The x squareds cancel out. I end up with negative 2x is equal to, and add 18 to both sides, and I get, okay, what happens when I get this? Positive 2, so I get x is equal to negative 1. Oh snap! I said to myself, there's no way I could get 1 because those two numerators aren't the same. What if x is negative 1? What happens when x is negative 1? Right? I was like, oh, those things can never be the same. Well, what is negative 1 squared plus negative 1 minus 20 divided by negative 1 squared minus 3 times negative 1 minus 18? Right? That's positive 1, and negative 1 is 0, so that's negative 20. And what is this? That's 1 and 3, right? 1 minus 3, what's 1 minus 3? Negative 2. What's negative 2 minus 18? Negative 20. Oh my goodness, that's a 1. So what is this telling me? What x will create 1? When x is negative 1, I generate 1. So that means on the graph, there is a point. When x is negative 1, y is 1, you would plot that point. Therefore, is y used by this function? Yes. 1 has been cleared. It was a suspect because it was a horizontal asymptote, but it must be used. Notice that the x value where it's used is a relatively close to 0, not as you approach infinity. So guess what my range is? All real numbers. Suspects were cleared. I had no holes, and the horizontal asymptote was cleared because there is an x value that generates it. If you don't believe me, put this function into your calculator, graph it, and look at the point negative 1, comma 1. Now let's look at this function. Example 2. What's my range? This time, what are my suspects?
All right, ready.
I still have no hole, but what's my ha? Remember, this is technically x to the 0. So I have an x to the 0 over a what? X squared. So since I'm bottom heavy, I have a horizontal asymptote at y equals 0. How do I know if I should kick y equals 0? So here's my suspect, suspect 1. Should I kick y equals 0 out of the range? Go to the equation and ask it. So again, I'm going to go over here and say, hello function, will this fraction ever equal 0? The numerator is a constant. How do you get any fraction to be 0 if the numerator is 0? Since the numerator can't ever be 0, the fraction will never equal 0. So what does that mean for my range? Up, convicted, y equals 0 is never used. If you don't believe me, graph it. I had my suspect, y equals 0. The suspect was convicted, so kicked out of the range. Doesn't get to come to the range party. What about this next example? Curious. Who are my suspects this time? Still horizontal asymptote of 0, right? But this time, I also have a whole. So the y value of a whole. Well, what's the y value of the whole? Since there's a whole at x equals 6, the y value must be 1/9. Truth? So I have two suspects. Use your cleaned up version. I mean, you don't have to, but it generally makes your algebra nicer if you use your equivalent expression, which is this one. And ask. Go over here to my workspace. First suspect is 0. Hello, fraction, will you ever equal 0? Again, my numerator is a constant. Who cares what my denominator is? No, there is no x that will generate 0, so my range kicks out 0. Convicted. Next, ask your function if you will ever equal 1/9. Is there any x that generates the y value of the whole? I'm going to reciprocate each side. Flip 1/9 to 9. Flip 1/x minus 3 to x plus 3, and looky, looky. Oh, I do get an x, right? I do get an x. Oh, therefore, I must be okay. I must be able to leave one. Oh, snap. Wait a second. Remember, I know that x will never, that the y value, right, at the whole, but I'm looking for, I wonder if there's another, I wonder if this function is not 1-to-1, in other words, and so there's another y, but what is the only x I got? That's the x coordinate of the whole. So that was kicked out of the domain. So since 6 doesn't exist for me, there is no legal x that gets me 9 here, which means there's no legal x that gets me 1/9, so therefore no, and the y value of the whole is also kicked out. Right? Kind of crazy. So that's it. Try your homework handout, and we will I will be there tomorrow, and we will check this homework as well. Again, remember, for last night's homework, please go watch the other video that I gave you in the email to clean up any of those issues. You want to get, the only way to get good at graphing these rational functions is by practicing them, and you'll get better. I promise. I promise. See you tomorrow.